Hello, welcome. In this short video, let us look at the CRB for the correlation of a observation vector. That is, given the vector xn that follows a normal distribution with the mean equal to 0, that is the mean vector equal to 0, in the covariance matrix C, where the covariance matrix is defined as 1, rho, rho and 1, where rho is the correlation. So, in this video, we want to derive the CRB for the estimation of or for the estimator of the correlation rho. So by comparing this vector xn, that is n is the index of the vector, so comparing this vector with the standard Gaussian vector x that has a normal distribution with mean equal to mu, that is the mean vector is mu, and the covariance matrix is C, you can see that mu is equal to 0 and C is equal to 1 rho, rho and 1, that is this matrix. And from a previous video, we know that the Fisher information matrix for a parameter theta or a parameter vector theta given this general Gaussian vector is defined as I of theta at ith row and jth column is equal to the derivative of the mean vector transpose with respect to theta I, C inverse of theta, derivative of mu with respect to theta j, plus 1 by 2 trace of C inverse derivative of C with respect to theta I, C inverse derivative of C with respect to theta j. In this problem, we can clearly see that the vector theta becomes a scalar which is equal to the parameter rho. So we are basically trying to estimate the correlation rho. So instead of a Fisher information matrix, we just have Fisher information, which is I of rho, which is a single scalar value, which is equal to derivative of mu transpose with respect to rho, C inverse, derivative of mu with respect to rho, plus 1 by 2 transpose C inverse derivative of C with respect to rho multiplied by C inverse derivative of C with respect to rho. And since mu is clearly equal to 0, the first term is already gone. So we have I of rho is equal to 1 by 2 trace of C inverse derivative of C with respect to rho whole squared, since these two products are the same. By using the standard formula for the inverse of a 2 by 2 matrix, we have C inverse equal to 1 by the determinant, which is 1 minus rho square multiplied by 1 minus rho and 1. So by using this definition in the Fisher information matrix formula, we have 1 by 2 trace of C inverse, that is 1 by 1 minus rho square multiplied by 1 minus rho 1, that is the adjoint matrix, multiplied by the derivative of this matrix C, that is 1 rho 1 whole square. So this becomes 1 by 2 trace of 1 by 1 minus rho square multiplied by 1 minus rho 1. The derivative of this matrix is clearly 0, 1, 1 and 0. And we have square of the matrix, which is equal to 1 by 2 trace of the product of these two matrices is given by 1 into 0 is 0, so we have minus rho into 1, which is the first term, and then 1 into 1, so the second term is 1, and similarly third term is 1 and the final term is minus rho. So the square of this matrix is equal to 1 by 2 trace of 1 by 1 minus rho square whole square multiplied by the square of this matrix, which is 1 plus rho square minus 2 rho 1 plus rho square. And the trace of this matrix is clearly equal to 1 by 2. The trace of this matrix is equal to 2 times 1 plus rho square divided by 1 minus rho square whole square. Therefore, the CRB on the estimated rho hat is given by variance of rho hat is greater than or equal to inverse of this term, which is 1 minus rho square whole square divided by 1 plus rho square. And when you have n vectors, that is when we have xn where n is equal to 0 to n minus 1, that is when you have n observations of these vectors, then the variance of the rho hat after n observations will become 1 minus rho square whole square divided by n times 1 plus rho square. This is true because the Fisher information basically gets multiplied by n when we have n observations of these vectors. Thanks for watching.